Hi, welcome to the OT Security, Operational Technology Security. This is lecture 3 on common ICT components. Okay, so why should we care about industrial control system or operational technology? Okay, so because there have been several issues, right? If you look at some of this business advantage state ICS in 2017, right? So many organizations have experienced a security incident, okay, for whatever months they have done through, and at least 16% have experienced 3 or more. So that's a very common incident today in terms of industrial control system that actually has impact by cybersecurity. The services is impact by cybersecurity. So what do we cover today? We'll cover the following item. We're going to cover some of the define of what is a industrial control system, identify all the various types, the data flow, and then the communication topology, okay, the method and the physical media. We look at some of the common protocol used in ICS as well. Okay, next. So let's start from the component itself. Okay, we look at the architecture and then we look into a segment in depth. So ICS, this is already went through, so let's skip this part. So there are several components ICS. First of all, there's a HMI, okay, then followed by the servers, few controllers, few devices, safety system, and engineering workstation. So what does it mean? Let's go one at a time. Human machine interface. So what does it cover? Right? It is basically a screen. End of the day, right? It's a graphical visualization screen, right? Just like your normal PC or whatever screen that you have. Okay, it is basically the entrance point that actually does all the control. Okay, the old name is called MMI, Man Machine Interface. Okay, basically it has the keyboard and mouse as an input that control the field controller. Okay, so there's a screen that all your inputs go in and then to control the field controller. So some of the name of a field controller is PLC and RTU. Okay, so that's one of the things. Okay, it can be either a touch panel or it can be just a web page or certain things that actually load onto a normal machine, the PC. There's a screen. The most important thing, the whole point of all this thing is nothing but a screen or a monitor. Screen or monitor. Okay, so that's the key portion. But it's smarter than the typical monitor. It allows you to do interaction and whatever. Okay. Next, we look at field controller. Okay, this is what just now we mentioned. The HMI control this. This is like your CPU. So you have a screen behind that have the brain behind and then do all the necessary stuff. So it takes in all the inputs and output and process it. So the key idea here is to do processing. Okay, and then it control whatever device that goes underneath it. So it get input from the screen and control all the devices. Okay, so that's where the thing is. Okay. Over here in terms of cybersecurity, they assume that all these devices are trusted devices. Okay. End of the day. In the cybersecurity world, it's not so simple anymore. So that is in terms of legacy wise. Even today, a lot of some of these devices is based on they just treat everything is trusted because all these equipment are not connected to the internet. Then, okay. Next, we look at servers. The servers allows storage or configuration of industrial control system. It allows remote access. It allows configuration. It allows information exchange together to the business network end of the day. Okay, remember this is factory network. Okay, but then it connects to the business network, allows all this configuration. So this is the server that do all this interaction between the business network and the factory network. Next, engineering workstation. So what's engineering workstation? To put it bluntly, it is a development environment. Okay. For the HMI, which is the UI portion, and then the field controller, which is the logic portion. Okay, so that is make up the whole entire process, right? Because you need to have a UI, you also need to have the logic, the software portion. So where to do the programming? Okay, inside engineering workstation. Okay, that's the key portion of what engineering workstation really is. Okay, next, field devices. Okay, so field devices, basically, we talk about this thing, we have to talk about the controller, right? The controller actually controls or receive information from this field controller. So what they get the information from? They get it from sensors. Okay, sometimes we call them instruments, or there is an in between. Sensor sometimes is what we actually mean here by sensor actually is transducer. Okay, the actual name is transducer. Okay, basically there's some processing and then it makes it digitally understand by a controller itself. Okay, and then the other thing is actuator. Actuator mainly is motors that actually do all the necessary controls. Okay, so that is an actuator. Actuator can be a switch, a valve, okay, or some other kind of actuator. Can be motor or can be solenoid. Okay, so those are outputs. I mentioned just now, input, sensors, and some other measuring instrument are inputs. Last but not least, safety system. Okay, safety system is helps to provide the safety for when the field device start running. So you actually need, on parallel, you need to have a safety system to make sure that if there's any emergency or any issue, the safety system will kick in. So that's what it is, to provide protection, because if the machine need to be stopped, the electricity need to be stopped, the safety system need to be there to kick in. Okay, it is a counter action for any critical operation end of the day. Okay, so when it's running, it will cause a loss of productivity, but then it is important that the safety system design always design traditionally design, okay, to be a separate system. Okay, but sometimes they share some communication protocol together. They're inbuilt together, depend on the kind of network protocol that you're using. Okay, so the core relationship, again, we repeat again. So your HMI is here. Your HMI is the input device, right? So see the arrow input going into the controller. So a controller can be a PLC or so on and so forth. It can be a RTU. Okay. And then this controller is a field controller. The controller get information from sensor, right? So there are two hard information. This is by human. This is by the actual reaction that you have. Okay. And then you make the necessary final decision and control the actuator. Okay, actuator can be, again, I mentioned motor. Motor is basically circular motion. Circular. And then you have solenoid, which is vertical action. So basically the solenoid is like you have a piece of metal here and you have some spring and it, like that, and then you have another electromagnet here. This is a permanent magnet, this is an electromagnet. Okay, so you power on, it will pull this thing into this direction. So it's a, if you release, then you will release, the spring will force it back to this direction. That's why it's a solenoid. This is a solenoid. Example, you have a pump or whatever. This is a solenoid, basically, end of the day, right? Cooling water or whatever, solenoid. Okay, so because end of the day, whether you're having a pneumatic system, air, or you're talking about hydraulic system, which is liquid, you can use some of these things to actually cause the hydraulic system or pneumatic system to function end of the day. So that's just an extension of it. The key portion of all these things can be electrical control and electronic control through a computation process. So this is internally here is nothing but a microcontroller. If you really think about it, right? Okay, that's all. Next, let's look into a different kind of field device. Let's looking into the more part of it. Field device can have meters, sensor, valve, switches. Okay. A controller can have these are some of the names for controller: PLC, PAC, RTU, IED, and then HMI can be workstation, SCADA, emergency management system. Let's take a look at a little bit detail. So few devices, right? We mentioned just now for inputs or whatever, right? And take a look at the signal. Now we are looking at the signal itself. It can be a discrete signal, okay, on off, okay, or analog signal. Basically, it can be any number, not just on off lah. Just be any number along that comes out, okay. Then all these are converted into finally a digital format, okay, ones and zeros, okay, because at the end of the day, that is where all these things finally, or whatever sensor will all this conversion will finally, we call them a transducer. Okay, there are some basic transducer possible out there. Basically, you can have a resistive, okay, through resistive functionality. If you based on the mathematical calculation, so it's a resistive transducer. Then you have a conductor, and then you can have an inductor, basically transducer. Of course, there is two more. One is called a Hall effect, and the other one is called Hall effect. And there's a piezoelectric. Okay, so this is they are all together, these 5 different type, the main 5 kind of transducer out there, okay, that allows you to gather information that can be done in a digital format end of the day, okay, in a digital format. The 5 major one, but most of them are these 3 out there, okay. Because of if you understand the basic design of electrical engineering, okay, so all these sensors get input. They can be a single number, single point, or can be a million point end of the day, okay, to do the processing. So all these convert whatever things that you have, whether it is a temperature, a pressure, some level, flow, some motor speed, some valve state, some breaker position into electrical signal, okay. It allows the operator to communicate and transmit all this information, okay, and be able to display all this format. So end of the day, the sensor can be, if you look from the information perspective, it can be discrete and analog, but finally it needs to be digital. Okay, it finally needs to be digital, because without being digital, it cannot be processed by a controller. End of the day, okay. So it needs to be able to become a digital, so that the controller can process, because controller is a digital device. It's a computer. End of the day. Next, so this is if you further look into the discrete analog portion, right? Discrete are giving on off status, on off, okay, and then it can be alarm or state and everything. Okay, it's either too high or too low, turn on, turn off, that's it, finish. Analog there's a possible a continuous process, all kinds of signal that comes in, right? Such as 4 to 20 milliamp end of the day. It's a range. Then of course you can change it to something discrete. Finally, I mean digital. End of the day, the most important thing is digital, because it need to be able to process it, and it need to be in ones and zeros. Definitely ones and zeros. Of course, ones here, it doesn't mean that it's definitely need to be 5 volt if you talk about a today processor, right? I'm not talking about zero, because if you look at the modern computer, for even more power efficient, it can go as low as logic 1 can be as low as 1.8 volt and 0 volt and everything. Okay, so this is the portion on the data itself. Similar, the output, it can be in discrete, it just on off, such as a circuit breaker end of the day. Okay, it can be analog, to be able to control the signal end of the day through either voltage or current. Okay, be able to control all the various valve, motors, or whatever environment that we have. Okay, it can be a digital output. A lot of time, whether it is analog, okay, or this discrete one, a lot of time it can come from digital. So you can do digital, can convert to this or convert to discrete. Very easy. Discrete is the same thing, just higher power, instead of 0 to 5 volt, right? It can convert into whatever voltage, let's say 24 volt, which is an industry system, to 0 volt. Okay, so this is the typical logic conversion, and especially it's very true when it goes to a lot of industry system that is 24 volt. Okay, next thing is analog output. So it just basically using ones and zero and reform the portion. The standard one is using pulse. Okay, electrical pulse, and allows you to form whatever kind of shape that you need, and be able to do necessary control. Okay, so that's the portion over here. Next thing is about field controller. The field controller collect data, process data, and send information to whatever field devices is doing. So it's close to the field devices, so it collect, process, inputs, and then also send data to output, and whatever completed already, it will also feedback to the HMI. Okay, so there's a feedback to HMI. Okay, it can collect and aggregate information from for larger systems, can collect from hundreds or thousands of sources end of the day. The key part is, end of the day, as I mentioned, it is nothing but a computer. Okay, is there a difference between an industry one and a normal one? Practically the thing is, it can take in higher temperature, that's all. But if you really ask me, is there a real difference? There's no real differences. Okay, the whatever component inside a controller and a PC is the same. Okay, because they are identical for cost saving and whatsoever, right? The key thing is, okay, you may say, okay, I have a DSP within my controller. Does your PC have? Well, a general PC can do, it's basically the mathematical computation, right? If you talk about fast Fourier transform, basically for their DSP, any PC will have that, right? So there's no argument about that. The specialty is no longer a specialty. Everybody has the same old stuff. Okay, so it's nothing new. Okay, it's nothing new. Most of the industrial controller came from a PC. Okay, came from the early days. You will talk about it. People are talking about running a 286, 286 system Intel to run whatever they need to run. So, okay, that's as old as those days, right? Then of course you have your 8051 and your the rest of other things your 6802 equipment. So all these are PCs, early days, 8-bit or whatever. That is very much today on your Z80, so on and so forth. So if you're talking about 8-bit, the 8-bit cut part of it, but well, modern days we're all talking about 32. Okay, so whatever you're talking about, they all exist in your PC. Few controllers, we can break it into a few different kind, right? If you look closely, one of them provide, now it's about feature lah. Actually, you talk about feature. Only one is slightly different. Remote terminal unit allows you to do remote access. It looks something like this. Okay. Your PLC looks something like this. So it's the main controller. Most of them are PLC. Okay. PAC is just some additional feature that comes with it on top of your PLC. Basically more RAM, more CPU, whatever, just a different name. That's a fanciful part. The really difference one between all these 4 of them is your IED, because it can handle a lot more voltage. Okay, so this is a lot higher voltage. It's used in an electrical plant. So this basically, if you really think about it, if you understand what are power electronics, then you know what I'm talking about. Power electronics. Okay, they're making use of power electronics to support whatever this thing. So let's say you are heavy industry, you're talking about a train. You need to have high power to drive the very high power. You're talking about 3-phase system and so on and so forth. Then you come into this era, this part on IED. Whereas if you talk about a single phase which cover 90% of whatever, then you're just basically talking about PLC and PAC, or you're talking about RTU embedded into a, nowadays there's not a lot of difference. I mean, in terms of all these things, they used to be very specialized things because they're very expensive. Nowadays, electronics very cheap. So, okay, yeah. The only leftover is how reliable is that particular component is. Okay, most of them are pretty reliable in terms of today's context, and they have more and more feature. It have blurred the differences between you basically, if you run TCP/IP, you don't really need RTU anymore because it's remote, right? Then your program is just more RAM and more CPU, so there's no difference between the PLC and PAC. But we don't really like to call PAC. Most of the people like to call them PLCs because something that most people are using. Okay. So in a remote processor, it allows to have a remote control interface, right? In the world of DCS, distributed control system, or SCADA, right, to allow to transmit data to master systems. Okay, and it allows to relay information over a long distance and support various communication media. Okay, various ICS protocol. Very proprietary end of the day, which is not favorable because it's expensive and difficult to maintain. So as time goes by, those days there's no internet. So today we have a thing called internet. So this thing is slowly gone as we go further down the road. Okay. Then so some of these things can respond emergency systems. So and they also act as a data concentrator and protocol converter. So well, today you talk about this thing, it's basically router and switches. Okay, in IT term. So it's cheaper to buy a router and switches than all this kind of stuff. And router and switches can perform a lot better than some of this equipment. So end of the day, these are some of the older equipment. Yes, you see this, but as time goes by, the newer and more newer equipment, this thing is gone, right? So what are sectors that make use of RTU, oil and gas, refinery, water wasteman, power electrical, right? Mine site transportation system. Okay, for air traffic control, railway and truck. If you want to have a specialized system, you can use this. But then expensive, right? So a lot of people choose to not go into this because this is designed in very early days in US, which they don't have. They want to have proprietary system end of the day. Okay. Next thing is intelligent electrical device, right? The key part, as I mentioned, power electronics is used in energy sector to monitor and control electrical power device. That's why I say power electronics, okay? Such as circuit breaker, capacitor, transformer, and so on and so forth, okay? These are some of the some of the things that it comes in with. It has a power relay device, protective power relay device, load tap charger, circuit breaker controller, capacitor, bank switches, recloser controller, and voltage regulator. So these are some of the common type of this IED. They are very specialized device, not in a normal place, but then certain sector would need to use them when it comes into operational technology. So they are high power equipment. So these equipment are specialized. You don't have a choice, because in terms of electronic, they are the one that can run through very high power. So they are important, and they need to be special at the end of the day, because you cannot just replace easily through. It's just not possible, because these are electrical devices at that level to do the control and what's so not. Okay. So many people leave their IED fresh out of the box, right? Default configuration, which is bad. Okay. And then there are some additional communication protocol, port active open, right, for them to do control. So a lot of these things is a concern for the cybersecurity world, because this is not properly done. So hopefully the vendor would put in more feature and allow to have better cybersecurity for this kind of things, because this thing, if it kills people. Okay, so IED is mainly meant for high paid technician that will not make sure that the will not have to drive potentially okay, to transmission to retrieve the data. So they a lot of time they do remote access. Okay, they plug into the RTU to do a remote access and everything. So there are terms and conditions on how to go about doing this, but then it is important thing that the cybersecurity take place over here. Okay, this is one of the more important portion. Next thing is PLC, which is a regularized computer, right? It's a computer, right? It can be inside an automotive industry, it can be in a factory, it can be inside a hospital, right? For a lot of pharmaceutical manufacturing plant, end of the day, because first of all, they make use of a thing called ladder logic to do programming. Of course, there's a standard to do this programming. There are 5 different methods to do the programming for this PLC. That I'll put it out towards the end after the lecture itself. The 5 different kind of way to do PLC programming. So these are the 5 different way. The first one is ladder logic, UI, low code base. The second one is the more common one, the structured text. The standard programming, like your C programming. So you have a if-else statement and so on and so forth. And then you have a function block, right? It's also a low-code system. You have one block and a block by itself to do the coding. It has a sequence chart, okay, function chart, and instruction list and all of this. So PLC today, PAC is a combination of RTO, PLC, and distributed control system. So basically, it's just a more powerful CPU, RAM, and all these things that allows you to do those things. No matter how low powered or how powerful the thing, today the main key concern is whether is it secure or not. Does it conform to cybersecurity or not? So some of this equipment, the bigger concern is, and then when they are designed, they should not just design in terms of robustness. Do they provide an underlying system? If they start borrowing things from IT that they understand what is outbound scanning for antivirus and so on and so forth, it will make them a lot more use in terms of cybersecurity a lot more better. Okay, so there is quite a bit of the things that vendors need to understand, that shifting to the cybersecurity portion is not just looking at just the pure functionality of the equipment. Everybody can do this. Okay, frankly speaking, a lot of countries can do this now. The more important thing today is the cybersecurity portion. Okay, which is quite missing from a lot of vendors. Okay, programmable automation controller involved in various critical infrastructure. Okay, can be used for discrete logic control, motion control, process control. Okay, the key thing is the RAM part lah. Okay, and then it has some of these things like HMI function, asset management, historian, and advanced processing stuff. So if you think about it, all these things can be handled if you have more RAM and more CPU processing, right? It can have more. It allows you to have more I/O. Allow you to add in more I/O, and then a lot of PLC nowadays allow you to have a lot of I/O. So what's the difference between a PLC and PLC? There's not a lot of difference at the end of the day. Okay, it's just a naming convention out there lah. Okay, so if you really think about it, now that's the last line that conclude. Have a more flexibility of programming, larger memory capacitor, better interoperability. So it's a more powerful computer. That's it. Okay. So it has a open architecture. Okay. It allows you to have a modular design. It's not one whole big block. It allows you to add, which is most of the PLC today can do that. Okay. It allows easy communication. Allows you to connect to standard network like Ethernet, which is TCP/IP again. Right. Last week what we went through, and some of the OPC protocol we will go through later, and plus database such as SQL. Okay. It runs in many domains such as motion control, communication, sequence control, process control, which are general most of these controls are. It can add and remove things easily by having I/Os and all this kind of stuff. Okay. So a lot of them we don't call them PLC, we call them PLC. Okay. Next, HMI. HMI is located in centralized distributed controls. You can see the GUI, and the operator would have a real-time or near real-time operational usage. Okay, when you're running it. Okay, operator, when you're using HMI, you want to monitor the process, you want to control and look at the historical trend, you want to look at whether there are alarm or event notification. Okay. HMI basically, from a cybersecurity perspective, it is quite an obvious target. Okay. And then because it's the main control, right? You can see right at the top here. Right? If you can control this thing, it will control the rest of every other thing that actually run it. So HMI has many command and control functionality. If it compromised, it allows the attacker to take over the whole entire situation. The whole thing. Okay, the HMI, sometimes we also call it a SCADA also lah. Okay, so the key portion is important that to keep the HMI safe, which is not very safe today. Why? The main reason a lot of HMI are not safe today, we cannot talk about all the non-industry based one. Most of the industry based one runs on a protocol called VNC. Okay, and VNC by itself is not very secure. So most of the HMI, when they are doing VNC, especially for remote access, they are not very secure. So that's where the whole of HMI really is, end of the day, the VNC portion. Okay. VNC is a protocol for, this is a protocol for remote access. Okay. Okay, so we kind of cover the general portion on the ICS itself, right? The architecture itself, that's the objective one. Next, we will move into a different type of ICS, big and small. So the first one we mentioned just now, SCADA, right? There are many different types lah. There are different requirement, diverse process based on their system requirement, process function, and business needs. Okay, so the first one is SCADA. SCADA is spread over a huge geographical asset a lot of time. They are using serial for communication, right? So, well, basically RS-232. Okay, RS-232 is basically 1:1 communication, and the speed is basically serial communication, which is 9006. Okay, even today, a lot of things we still run at this particular speed. Okay, well, in a control system, it doesn't need to have a lot of bandwidth. What you want is low latency, because the information sent is not a lot, but then the information need to be real time, low latency, as real time as possible. What do we mean by low latency? Okay, you understand what is 1 second, right? So your T, when you have certain things run, right? T equals to 1 second, which means that our process will take 1 second to finish, right? What do we mean by this is the latency? Even you have 9,600 bit per second, if it takes 1 second to finish, it takes 1 second to finish. Okay, so the next level down is 1 millisecond, so 1/1000 second. So that is 3 factor smaller than your 1 second. And can you do 9006 under this kind of latency? Right, that's one way to look at it. Then on top of it, you can look in terms of 3 microseconds, which is 1 of factor 660, or even 1 nanoseconds, a factor of 9 zeros. Okay, so that is the difference we are talking about. Okay, typical system in the normal latency is in terms of millisecond. This is normal. In a low latency, we are talking about at least at microseconds. Okay, so at a factor of 6 zeros. Okay, the CPU will need to operate at this level, because this is what we call 1 gigahertz. Okay, a lot of embedded system the old embedded system cannot handle this. The newer embedded system can handle this. Okay, we are talking about things after 2020. Okay, things that is after 2020. Okay, can handle this easily. We are talking about microcontroller, very low cost, but then we need it to be very powerful. Okay, they are mainly here for a long period of time. So whatever that you see from year 2000 onwards are mainly this. Then the millisecond one is pre-year 2000, pre-millennium. Okay, pre-2000. Okay, in terms of milliseconds. Now we are looking at microseconds, so low latency system. Okay, so that's what the importance of the system today we are more and more talking about end of the day, because you have more and more equipment that you need to talk about. Okay, so we come back to the SCADA portion, right? And digital data improve the network, extend to more remote, and they can do more things today, right? But then if they are not properly maintained, is subject for cyber attack. Okay, so there are a lot of data that it collects, right? If a communication field, the field controller must individually control. Okay, there's a few ideas here that things need to talk about. Okay, most important thing, we don't want to have all these things to fail, right? Because SCADA is a major system. So we'll talk about loss of vision. Okay, loss of control and loss of safety. Okay, loss of vision is if they are connected and cannot see anything at your SCADA level, that's loss of vision. Loss of control is more serious, right? Few controller must be individual control. Okay, they need to have some form of automation themselves. If you lost that, that's even more serious than loss of vision, because you cannot see that thing is lost control. It may kill someone. The thing definitely will kill someone is loss of safety. Right? Because that's look at from the work perspective. So that's the portion that in terms of cybersecurity, this is a different level of things that we are looking into based on the design feature, right? So it should not have loss of safety, it should not have loss of control. Well, because you cannot design a 100% system, so as much as possible you want to think from that perspective and design the system end of the day. Okay, so there are many commonly used from SCADA. Today a lot of SCADA is connected, not just we mentioned just now, RS-232. All the numerous SCADA system is through over TCP/IP, your internet. Okay, so it's used by electrical system, oil and gas, drinking water, wastewater, and transportation system for SCADA. Okay, it stands for supervisory control and data acquisition. Okay, how does the architecture look like? Okay, if you take a look, so this is how a SCADA system look like. So it typically connect to a wide area network, huge area network, and then you have workstation, production system, right? And then you have server and corporate things. When you start thinking about this thing, right, then you have your main SCADA server here. How would this SCADA thing end of the day that can use, if you understand what the heck is RS-232, right? It used to be controlled. The few controller and the host computer are through RS-232. So are they network or not? Even network. They are not network. Okay. The key part is not just RS-232. RS-232 is just a document here. Most of the thing is, yes, you're talking about a single machine that's not networked. Okay. Thereafter they are doing network. A lot of them are RS-485. Okay, that allows what you see this thing possible. Okay, so a lot of this in the process area, right? Where's my mouse? Okay, all this process area thing, right? And all this process area thing or whatever here, right? They are all connected to the machine through RS-485, which is what we call multi-drop system. Okay, when I talk about let's not talk about that. It is basically multi-drop. We are talking about in terms of in the 90s era. In the 80s is basically RS-232. Okay, that's how old the thing is. When it hit 2000, okay, what comes in? Internet. Okay, internet comes in what in the mid 90s and 2000. So internet comes in at this point in time. Your TCP/IP. Okay, cannot be earlier than that. Just that does not work at all. There's no such thing as internet then. Okay, so that's the progress. Then and even if you talk about 2000, it's 20 years ago. Okay, it's that long and that old of a system. Okay, so then in year 2000 there's not a lot of cybersecurity, by the way. Okay, so what you see here as a picture came from historical design. If you really thought about it, is from year 2000 or so. Okay, this diagram over here. If you really thought about having supervisory HMI, corporate, and all these things, right? And all these things come at after year 2000. Okay. Next, distributed control system, right? It is initially developed to support large process industries such as refineries, pharmaceutical plant, okay, chemical plant, used to control or distribute throughout all the plant. So it's called distributed control system. Okay. The key difference is it has it has one machine or many machine to controlled by a single controller. So a controller can control many systems. So it is pretty powerful in terms of the CPU wise to do that, right? The key portion is, you say, what's this difference from a PLC? It's no different from a PLC. The key difference is it can have multiple controller dividing the task out, and then they can take individual part end of the day. Okay, so you can have multiple controller controlling multiple device. So it's a many to many relationship between the controller and the devices. That's the key difference of this distributed. If you talk about normal PLC, it's not a lot of time. It's 1:many. One controller versus many devices. In terms of the architecture wise, in terms of design wise, okay. Then what are the common use of this DCS? These are some of them: chemical, water treatment, rail transit, power station, petrochemical, pharmaceutical. Okay, BCS. Okay, so then in terms of architecture, let's take a look. So they have some of these: one, general workstation, operating system, smart device, and communication. So this is how it kind of look like for a DCS system. So you can see there are several controllers, right, and then they control many devices underneath them. So there's a hierarchical system underneath here. Okay. Then you may say, how much difference is this from SCADA? SCADA is over, remember the key part, over a big area. This is typically within a big factory, a huge factory. Okay. So if you really think about it, SCADA is a data gathering system. DCS is a process-oriented system. Large geographical area for SCADA. Over here is confined to a area which is local area network. When we talk about local area network, we are talking about less than 100 meter. This is we're talking about greater than 1 kilometer. Okay, so that's some of the difference, right? It's not a closed loop system. The sensor may not come back for whatever thing, right? Closed loop means that I have whatever control I have done, my control to my device. Is there a relevant sensor inside here that give a feedback? That's closed loop. That's what DCS is. There's my mouse. Okay, that's what it is. But then SCADA is not a closed loop system. Not necessarily need to be a closed loop system. Okay, it is event driven, right? And then it just wait for some event to trigger action. Okay, if not scan ordinary. This is process driven. Okay, it scan the process. Look at the process. Okay, and then it also can do on demand. Okay. So you may ask, what's the difference between event driven? So if there is a thing that triggers, right, certain thing stop, certain thing runs. So event driven. Process driven. What is the process? You will actually have a process is during the process. Remember the last week we went through, the 2 weeks ago we went through a process, right? You can have a certain liquid or whatever. It need to continue to run, and then where the state is at that point in time, you need to add in, you need to remove. It's continuous. this is on and off discrete. This is discrete. This is continuous. Remember, can be break into parts. It's on or off. That's it. This one cannot on or off. This one is controlling, or how many is the level, right? Is it 80%, 90%? It's not on off. Okay, so that's the key difference. Okay, this is used in large geographical location. This is used in a confined area. Okay, so that's the key differences. I hope I clarified this SCADA and DCS. So then process control. This is even more functionality, right? So it runs like a DCS. The architecture is look like SCADA. Okay, architecture wise, but it is make use of the best of both worlds at the end of the day so it can do continuous batch and discrete processing end of the day. That's why we call it the PCS, right? Because at the end of the day you may have discrete processing, because you may have one to do on off one. You want to do on off, then how? Then you have a DCS, you cannot do on off, right? Immediate on off, right? So there's a thing called process control that can allow you to do on off. For certain systems, they just want to switch on or switch off just on the fly quickly. Okay, so a lot of them are just a repeat of whatever DCS is lah. Okay, and DCS a lot of time are for big refinery. This PCS is more common. You can use it for no matter what kind of size. So a lot of time they are inside a PLC itself, so you can make it quite a small system end of the day. Okay, and then well, today less and less people are doing SCADA. More and more people are doing PCS system, because end of the day is through the network itself. Okay, it's doing computer network end of the day. The traditional IT network. Okay, so this is the process of what is going on over here. There's a controller that controls the actuator, and then the process. If you look closely, it is closed loop, right? Like DCS. It's not like SCADA, right? Architecture wise. But then because there's a feedback, right? That's why I tell you the feedback portion. But then it allows you to do discrete, right? Which DCS don't. Okay, so that's the key difference. Now we have done the first two objectives. Let's move to objective 3 now. So what's objective 3? Objective 3, we are going to discuss flow within the ICS and the ICS process. So what do we mean by process data? Okay, process data over here basically means that we are designed to control some the chemical process or physical process of our upstream and downstream. So it's continuous system. We want to do it. We need to accurately and timely do the measurement to the monitor and control, and we will do all the necessary changes. As I mentioned, it is it's like 80%, 90%. Where are we? Right, it's not on off. Okay, so there are several devices such as low level temperature and pressure are things that basically for example, in a water treatment plant, we need to know the pH or the turbidity. So you have an instrument that allows you to measure some of these things, or it can be a flow, a level, or pressure level, and what they for clean water. So some of these things require all this constant measurement to meet the specification. So what is involved? So these are the things that's involved. Okay, for whatever it is, it does the whatever collected goes inside there, and then output to all this. Okay, end of the day, because you want to track to meet the thing. You may want to open a valve, close a valve, so that the pH level is correct, the turbidity correct, the density correct, the weight correct. Because When you measure, the sensor give you all this information, but then you can use flow, you can use level, temperature or pressure to control the necessary stuff. Okay, so that's the key portion of this processing of data, right? The who is doing this thing? Of course, the PLC is doing this thing, the computer the brain is doing this thing okay. So there are various kind of loop inside there. The basic one is called a single loop control. Okay, just like what you saw, I show you this thing something like that. This is a single loop. This is a single loop. Just there's only one loop, one loop. Okay, this one loop. There's a single loop. Okay. Okay, for that, and there may be some devices, sensor, and measurement or whatever not. Okay, and it may include a human being inside the loop. So this is a standard process flow You have a HMI, okay, and then you have a few controller, your whatever data. This is the feedback for the few devices, and then update to the HMI, right? And then you will control the actuator. Of course, you can get information from the HMI also, which is right at the beginning. There's a diagnostic system that at the end of the day send information to the this part, and sometimes you look at the diagnostic of this part. In order to diagnose whether these two things function properly or not, it gets information from the controller. Okay, the actuator, eventually the data would actually feed into the control process. Okay, the control process, the keyword is control process, so that at the end of the day you know what's going on. Then you have the process output. Okay, so beside a single loop, it can be a cascading control, okay, or cascading nested loop. So it's a loop within a loop. Basically, you have some information that goes into a controller, and then you send information out. Then you have a second part, right? The second controller. So the second loop comes in, right? This is a second loop. So this information comes from one loop. It goes in, and then it's supposed to have some feedback part, right? It's not immediate feedback, so it's a indirect feedback already, right? Through another controller. Okay, and then there is this part itself is a loop. This is one loop, right? This is one loop, and then there is a bigger loop here. Okay, so that's a nested loop. That's what it means, right? Cascading loop. Let's do a proper drawing again, So this has a loop, right? There's a valve here, so there's a loop here. Then there's a bigger loop, because at the end of the day this information goes in, so this one will go as a bigger loop back, right? So there's two loops. It's a cascading loop. That's what it means, right? Because you want to get information, get the water flow here, and then some of the information to make sure that whatever here is the correct feature. So there are certain systems that require to be that. Okay, there are certain systems that need to be that. Data flow, okay. But nowadays it's possible to process the whole damn thing together. It depends on how you design this thing. Okay, it depends. Sometimes it's not possible. Okay. Next thing is data flow through ICS by vendor, topology, and protocol. Okay, the data flow, how each vendor they communicate, the way the network is, and the protocol. Okay, the key thing is HMI receive information from controller, and then relay the information through communication protocol to provide the operator what's going on. Okay, what is going on in the field of it. So this is a design of a flow, right, of the HMI portion. So all these are HMIs. Okay, all these are HMIs, right? You're talking about information that gather all these things, right? So your controller actually feed in information to this HMI. This HMI need to be updated to a database and eventually go all the way up to the that's where the data is, right? Eventually you have to go all the way up to the secondary historian. There's a primary historian. Okay. The configuration path is the dotted line, right? The database actually do all the necessary configuration. And where does it get information from? Well, through the field controller, but then via the field controller, but then HMI actually activate part of the information. Part of the information comes from the field devices. Okay, so this is the design for the flow. For certain flow, will look something like that. Okay. So field controller is the one that actually consolidate the data and transmit to HMI and present the data where it is. Okay, which is here. Okay, over here. Of course, you have a SCADA system, then goes to a SCADA system end of the day. Okay. So, that is the part. This is a clean cut from exactly what we are covered in week 3. Okay, the third lesson. So I shall move on and start covering things on week 4 at this point in time. Okay. So welcome back to operational technology security. We are going to start covering things on week 4. Okay. So objective 4. What we're going to cover inside objective 4, we are continuing. Because 3 and 4 is one subject by one lecture size by itself. So we're going to continue the ICS information. So we will cover the kind of the device, the data flow portion. We are going into the communication portion of the ICS protocol itself. So we're going to look into some of these things like ICS topology, polling method, field, master and slave relationship, and the physical media. Okay, so these are some of the things that we're going to cover. Type 1, right? ICS is very similar to IT topology. Basically, they copied the damn thing from IT. Okay, in terms of the network itself. Okay, ICS requires some form of redundancy out there in comparison to IT topology. Okay, which is not commonly in IT lah. That's what it says here. Okay, so a lot of ICS are using a lot of proprietary technology that is not in the IT domain. End of the day. Okay, so that's one of the key portion. Next thing is there are a lot of serial technology out there. Still today, there are a lot of serial technology such as RS-232, just now I mentioned. RS-85-232 is one point-to-point. 485 is multi-drop, basically allows one to many. Okay, and then Ethernet is a modern one. As I mentioned, this thing is like 80s, 90s, and then 2000. Your Ethernet. Okay, so every kind of 10 years, the improvement comes in. So for serial connection, it's not possible to have bus topology or whatever lah. So all this refers to Ethernet. Early days Ethernet, right? Ethernet can be in bus topology, which is 802.3. Can look something like that and allows you to connect several connections together through a coaxial cable. Okay. Then there's a thing called token ring, which is 802.5, right? So when the machine want to talk, they'll go by, oh, this machine can talk, then followed by this one, followed by this one, then followed by this one, followed by this one, then last but not least. So that's a logical portion of it, so it can run in this manner. Okay. Whereas a bus is, who want to talk first? Oh, I want to talk first, so he sends. The rest keep quiet. Then who want to talk next? This one can talk next. So it can be a lot more random. This has its own advantage because it's random. You don't need to wait until your time. So for certain under certain construct, this can be this is because of that's how internet is. Today most internet is. So this is a lot more efficient when you really compare to a ring-based system. Okay, because you don't need to wait. Okay, but then of course there are certain sacrification here lah. Okay, there's a certain sacrification here in terms of the network, but then is negligible. This is more deterministic. This is less deterministic. Okay, so that's where the key differences is. Star topology is basically you wire out everything into a wire box, but internally is either a bus or a ring. Okay, a lot of time. That's what star topology really is. End of the day. Okay, it's internally it can be a bus or a ring, but then externally it's just a connection is in this way. Today, most of them are bus, ring, not that much anymore. Okay, because the way it's been designed, ring is very cumbersome. So end of the day, you need to have two cables if you want to have ring. But bus, you just need a single cable. End of the day. So I mean, you can ring. You want to have a single cable is possible lah. But then internally, you want to at the logical level, you need to split into two lah, right? You need to have two. Because ring, right? How do we have a ring in a star? Just need to do like that, lor. Isn't it a ring? It's the same, right? Just everything under a cable, wire box, end of the day. So it's two cable here, either two physical one or two logical one. That's it. Okay. Next thing, polling method. Okay, polling method is very common for a lot of IT system or computer system, because you want, for example, your mouse and your keyboard. Basically, your CPU will trigger an interrupt and ask them, mouse, do you want to send information? The mouse says, yeah, I want to send information, and you start moving. So there is a between a master and a slave condition that you are controlling. So it's the same thing for your keyboard. So the CPU constantly asks, keyboard, you got any information on? You have, okay, then you send the information. You have, and then you send the information. So it's to a regular state that do these things. Okay, internally, if you really talk about it at the hardware level, is either a thing called what we call interrupts. Okay, at the processor level, at the microcontroller level. Okay, so it's either a hardware interrupt that tells you, oh, how the polling going to do, is either hardware design or you can program it. Programming is slower lah, then that's called software interrupt. Today, if you're using a Windows machine, internally there are a lot of software interrupt. Hardware, you have limited how much is it. So most of today one is a software interrupt. Of course, you can reuse the hardware interrupt for whatever it is. Especially for ICS system, a lot of them are hardware based in terms of the interrupt wise, because you want the speed, you want the low latency portion. Okay, so that's what the polling method is here. The key thing is to interrupt and then be able to send response. Okay, so the controller relationship, right, depend on how fast or how slow the thing is. So you can poll twice a second, or the lower devices can poll once a minute. So they're just polling them and ask them, do you want to respond or not? Whenever they are doing this thing, the rest of the thing don't run, but let's just run that particular portion. So that's where the interrupt comes in. Okay. Then you can have a direct connection. Okay. Some of them, like, so this is a direct connection. This is RS-232. This is multi-drop. This is your RS-485. Then your multiple master can only happen in whether you're talking about Ethernet. At the lower layers, Ethernet lah. On slightly higher layer, they call them the Ethernet IP or Profinet. There's Siemens, there's Omron, and then there's a EtherCAT. If you really need speed, then EtherCAT. Okay, so these are the few industry protocol or operation technology protocol that is used for these purposes. So basically all of them are Ethernet. If you really think about it, at for that perspective, if you want to run multiple master. Next, the physical component that connects them together. When you talk about Ethernet can be the early days of copper cable. Okay, Ethernet are basically copper. Okay, and what kind of copper? The very early days is 75 ohm coaxial cable. Okay, it's a specific cable in the day. It's a very thick. It's a television cable. If you've seen the very old television cable, that's what Ethernet is running on. Okay, it's a very thick cable. Not like that lah. It have a ring and a ring and a ring in the center. Yeah. So this is what a coaxial cable actually look like. Okay. Then slightly modern one, you have twisted pair. Okay. So you have two. You have your modern Ethernet cable that you see that very small, and then you have a this is a plastic cover here, and then there's a twisted pair, because there are the part of two of here actually twist. Okay, so that you reduce the signal. The coaxial by itself is thick because this is thick. This is quite thick. A coaxial cable is thick because internally they are grounding to cancel off all the cross signal. Okay, so it allows to carry a lot of bandwidth inside here. The thick cable. This is very thin. This is much easier to do. The twisted pair. Okay, and therefore it cannot go a long distance, but then it's very effective to lay all this cable everywhere. Okay, so at your home, most of the modern home in Singapore, you actually this is the same as your telephone cable. It's just that instead of 4 cable or 6 cable, this is 8 cables. Okay, that allows you to go up to about if you have a Cat 6, they have different category. Then it allows you to go all the way to 10 gigabit per second. Okay, this doesn't obviously don't go for the bandwidth. This go for distance. The coaxial go for distance. Your old cable TV is this. Okay, StarHub. Okay. Then what else? There are various other things such as a dedicated line, lease line, power line. In terms of RF, wireless, radio frequency, microwave, cellular, and Wi-Fi. Okay, let's go in deep a little bit deeper. Lease line, what is lease line? Lease line basically is a dedicated communication circuit provided by the phone company. Okay, you're leasing from them. Okay, the lease line. So you lease a connection from them. There are very old ones, such as X25, X.25. Those are the early days lease line. Okay, this one protocol we talk about. Then you will talk about slightly modern one that mainly Singapore is using, because you still have to come back to Singapore. So in early days, what we have is we have ISDN. Okay, integrated service digital network. Okay, so the standard, they have two rates. One is called basic rate, one is called primary rate. Basic rate is 2B plus R, 2 broad and 1 not so much. This one is the one that is 16 kilobit per second. This is your 64 kilobit per second. This one has a Europe version and a US version. So a primary rate here, it can be 23 plus R or 31 plus R. Europe is 31, US 23. So this is a T1 line. We call it T1 line. So a certain bandwidth, 1 megabit or so. And there is a E1 line. That's about 2 megabit or so in terms of total bandwidth. I mean, you just calculate 1B is 64. B is 64. R is 16. Okay, and this R thing eventually is used for in cellular, used for SMS. Okay. Okay, so basically they are the lease line. Okay. A lot of lease line, why telephone network? Because telephone network end of the day, they're providing every line, they're providing at least at about somewhere at 64 kilobit per second. So the line actually can provide 64 kilobit per second. Basically, a set of twisted pair that give you 64 kilobit per second. Okay, but then the 16 one is not so good of a out of there, not the line is not so good, not so clear one. Okay, then there is the 16 kilobit per second comes in. Okay, so all these are early days copper cable. Okay, copper cable. There's also possible to run the dedicated line. Okay, basically you dig your own road and then you lay your own line, and that's dedicated line right? Very expensive. Okay, the dedicated line is very expensive. Okay, of course, in old days there can be two kind. This line can be an analog one or digital one. The one I'm talking about, this ISDN, is a digital one. I mean, no point of talking about analog one. Analog is basically your PSTN network. Okay, public switch telephony network. Public switch telephone network. Okay, I shall not go too much in detail to this thing because this is a very old network that no one is using anymore. Okay, there is still people using it. Basically, if you want to have a telephone to your home, you pull one of this line. It's called a toll line. But even Singtel, StarHub, and one, not a lot of people want to support this thing anymore at the telephone because it's very expensive for them. Because they're pulling whatever there is, so they actually keep a lot of the no longer having this analog line. In US, there's still quite a bit of this but then it's slowly dying off Okay, rest of the world, we are also not using ISDN anymore because this is actually narrow band, not a lot of bandwidth if you think about the total bandwidth that provided here, right? The key portion, all this is in the 80s in Singapore. When we hit somewhere in the 90s, late 90s or actually 2000 I would say 2000 which is somewhere like then Singapore wide, because between here to here we are pulling all the fiber now. Okay, so that fiber have a lot more bandwidth end of the day, much easier to maintain, because end of the day you don't have a huge bundle of copper cable. It's just one thin little fiber, because fiber end of the day, because of the nature of fiber, it reduces the core, the size, the radius of the cable itself. It does not need to be very, very thick. Okay, copper need to be very, very thick in order to achieve more and more. And then if you want to put in more and more bandwidth and you need really a lot, and it's going to be very, very, very thick. Okay, but then as fiber, it can carry a lot more data bandwidth than copper. Okay, so that's where the thing turns into. Lease line are more secure than dedicated line. Obviously, is more dedicated than lease line but then the thing is the cost of it is very high, very expensive. So as I mentioned, Singapore has moved on to, actually the whole entire world has moved on to fiber. Okay, copper is slowly removing. It's only at the end point that you see a copper cable. The backbone practically I would say 80% are all fiber now, because it's a lot more easier to maintain than copper. You're not going to have you don't have a lot of space, and then it's very hard to maintain another thing, right? Because too many cables, you don't know which is which, where is where. Of course, there is still copper cable. Just to finally tell you, there is still copper cable. Okay, it's only left the analog portion, the one that is used for your telephone only. Okay, rest of it is all digital one, are all slowly shifting over to fiber itself. Okay, so there's a lot of environment doing that. Okay, because they offer fast, reliable, inexpensive services, right? uh, Fiber optic cabling is known to harder to tap than copper. Okay, it's harder because you want to, in terms of what does this mean? Means that if you want to steal information, fiber is better because it's very difficult to do, but it's not impossible lah. It is not impossible, right? But people run into a risk of there are a lot more risks if you start tapping into optical fiber. It is possible, but then you're running into a lot more risks. Basically, if you're a hacker, if you look at a copper, you will think twice and 3 times before you actually do the tapping itself. Tapping means that you are sniffing into a traffic and see whether they can steal information from there. Okay, it's really a lot more. It's a lot harder. It's about easily 10 times to 100 times more tough than copper. Copper is just cut, disconnect, and then join it back and put it in another copper cable. You can find it easily. Fiber, it is that's the machinery. You need to have a specialist just to use the machinery to do a cutting. Okay, so it's not as simple as a copper cutting. It's a lot more complicated. Okay, it's really a lot more complicated. You need a very highly specialized device because of the nature of how copper is being designed. Okay, next thing is on power line. Okay, power line also is a copper can carry transmit data. Okay, on electrical conductor. So there is a standard on there. Okay, because power line is everywhere, so it is people like to use power because they allows you to collect the data, whatever it is. It's not so easy. Not every country provide this feature. Number one, okay. Number one, not all countries provide this. Next thing is why not every people want to do that. It's easier to basically it's easier just to do fiber. If you want to use power line, you need to make sure that your power line, that power line is a lot more expensive than your typical power line that you are running for many countries, because the purity of the copper, the way to lay the copper cable, and the connection of the power line need to meet to a much more stricter standards. Because if you don't do that, your data will not go to whatever places that you want to go to. so of course there are some countries that use for the electrical, gas, water, like in US, may adopt power line communication as a mean for the information itself. But it not necessarily need to do that okay. There are many ways of doing it. One of the easiest way is for our wide area network, right? Then you use SMS the old way. It's a lot simpler. It's just using whatever that you have on your data network and then just connect to it. That's it, done deal. Okay. Then people will say, oh, if you go to gas and you put the SMS, will it explode or whatever or not? I don't think you need to worry about it because all this meter is not a direct tap to the actual device itself. So the meter, after a few cycle up already, right, then you pull the actual data, you extract out the data, is further out. So it's not so much of an issue of using SMS. It's less, and it's a lot easier to deploy this than power line itself. Okay, so there are many a lot of solutions. Is most of the solution are SMS instead of power line. Okay, so not a lot of countries do this end of the day. Okay, of course it's possible to do it for HVAC and control for lightning and whatsoever lah. There are such a thing out there lah. Okay, even for Singapore lah, but then the because of the nature of power line, not everyone are doing that lah. By the way. Okay, then it's possible to do obviously other things such as broadband over power line, right? They give you the same speed of DSL. Yes, and then there are some of the other things such as power line communication in Europe, right? It's possible to do this broadband over power line. So, okay, some of this system is still there, but then they are not very widely used. Okay, end of the day, because if you see, okay, has not been implemented in US on a broad scale because of signal degradation, right? Correct. so that's the part lah. It's not easy to do it. So end of the day, it turns out that it is more expensive than just running SMS, which is a lot more simpler, a lot more maintainable, and a lot more lower risk. So end of the day, even SMS, people don't do it for gas or whatever. So end of the day, you only get it once an hour, just a normal digital connections. Next thing, wireless radio frequency is nothing but what I mentioned here is basically just now all those are wired lah. Wired is contained, so it's easier to do. Wireless is not so simple. So what we are talking about here is wireless. It's more than 300 gigahertz or whatever we're talking about here lah. Okay, so there are huge spectrum allocated for all kinds of purposes at wireless, right? For operational purposes, it also used. I just mentioned only SMS is one of the early days and the most used way of doing all this kind of data collection, controls, or whatsoever not. Okay, SMS is one of the very highly used one. It only needs to run. Basically, SMS is for you is 140 character, correct? Just now I mentioned the 2B plus R. The R, this thing is 16 kilobits at the back end is 16 kilobits per second for ISDN. Okay, so today we are they're still using the R portion, but then it depends on how you break it out. Like if it's not a copper anymore, fiber, then you just provide similar bandwidth lah. But then you can provide a lot more lah than this lah, right? At the wire end, okay, you can basically provide a lot more than this at the wire end for fiber. Okay, you just need to allocate end of the day how much bandwidth you want to do. Okay. Then obviously the next thing is microwave and cellular. You don't see they talk a lot about this thing because US is not very good in cellular network and all that. Okay, but I talk about rest of the world. Singapore is doing yeah. Then you have GSM. We killed GSM. So there's as I mentioned, there's a 2G, right, which is GSM. Okay, this one on 800 megahertz, 900 megahertz. 1008, 1009, 2G 2.5G are same technology, which is called GPRS. Okay, 2.5G. The only difference is in 2G is basically your transmission everything. At the lowest end is all analog lah, by the way, but then halfway between you're just transmitting all the voice. Why am I drawing here? This is what we call time frequency modulation. So you have, this is frequency, this is time, and so everybody are sharing, each user is sharing one slot inside here. Okay, so by frequency, by splitting by frequency and splitting by time, the time is very very micro lah, because you are using atomic clock. End of the day, you will not differentiate because it's running so fast. You won't differentiate. You will not know that you're splitting by time, but you're still splitting by time and by frequency, which looks something like this. Okay, so with that, right, some of them you can turn it into. It used to be you have to do another level of modulation. Basically, modulation means that you convert whatever data to voice, then traffic, and then which is only give you, each of these is only giving you a 8 kilobits per second transmission, and then finally if you bind two of them together, 8 kilobits per second, you get about 16 kilobits per second because the voice part is 8. So bind two of them because eventually you need to remember the lower the at the you get about 14.4 kilobits per second raw traffic for GSM. Okay, this is the raw speed for that. But then if you not doing a conversion to voice, which is here, your data to voice, and you straight away allow at the network itself, there's a thing called packet separator. Okay, this is what the 2 GPRS is doing, and you don't use the typical traffic such as a MSC or BSS. Basically, your GSM architecture, you're using a GPS architecture, basically their own router, own switches or whatever, 2.5G, even though they run on the same frequency, right? Because in this kind of network, they have 3 parts. They have their base station portion, they have your network portion, and they have operational portion. So 2G GSM has this whole lump thing, but everything is analog. The GPRS part, they have a thing called packet separator over here. Over here, this is the packet separator, and that allows to boost the bandwidth to a total bandwidth of 171 kilobits per second. Okay, that's 2.5G. And then your 3G would provide you a 2 megabits per second bandwidth, and 4G 50 megabits per second bandwidth. Okay, so in terms of that for the design portion. Okay. So that's what the cellular network is about. Of course, your 3G is a separate frequency altogether, so it runs on 2100 megahertz. So it's a separate antenna, so everything is data. 3G is everything data. 4G is not just everything data, but multiple antenna. Okay, so your GSM, you have to share your GSM and GPRS is shared all this frequency with the voice. Okay, so 2G shared with voice. So there's a limitation. The maximum you can get is this. Okay, because there's a mechanism to separate the packet, and that's it. 3G new frequency, but one new frequency, one antenna. Okay, one antenna. 4G is multiple antenna. MIMO lah. We call them MIMO lah, same as a Wi-Fi. So multiple input, multiple output. Okay, so multiple antenna. So multiple frequency, and then because that, then your bandwidth be able to transmit a lot more than what is possible. Okay. Next, we move to objective 5, the common protocol used in ICS. A lot of this thing is at the if you talk about wide area network. Now, next part, all these communication. Then we come back to the short one. Cable, right? We go from very short, then we go for the long distance one, right? Then we come back to the short one, all the short protocol. Basically, it cannot be your RS-232 or your, what I call it, the RS-485. Basically here, either sit under Ethernet or mini this or IP or the Profinet, which is Siemens, and the other one is the EtherCAT. Okay, most industry are using this. Of course, there's a one whole lump lah. Later we'll go. I can go through some of them lah. But then, these are at the baseline. The lowest level is basically Ethernet. Okay, because it's less than 100 meter. Okay, most of this protocol we are talking about is for that purposes. It doesn't go beyond the so-called more than wide area network. Wide area network by itself, all these things runs its own network. Power line run its own network. Okay, so all these are run on its own network. Okay, so okay, then we go down to over here. So communication channel. So it's just a transmitter, receiver, basically local area network lah over here. Okay, then there's a communication between them. So you can basically using low cost Ethernet and TCP/IP, replacing a lot of auto proprietary protocol end of the day. So today basically it is. So it's not so easy to have real-time systems eventually. Okay, so Ethernet by itself is not exactly real-time. That's why there is a thing called Ethernet. There's a thing called EtherCAT, but this is proprietary lah. Kind of proprietary end of the day. Okay, this one will give you a lot higher in terms of speed, because this and this is not entirely compatible one another. EtherCAT is something like cellular network. We call them, in terms of networking, we call them isosynchronous protocol. Whereas this is just a synchronous protocol. Okay. Asynchronous means that you don't need to do synchronization. There's no timing, right? There's no timing. So anyone who want to send and receive, you can through the Ethernet, the standard Ethernet, right? The old one, okay. This one is because there is a key timer at the master, and then all the slave will follow this master timing. But then all the card need to be changed. You cannot use a normal Ethernet card anymore. It's a non-standard Ethernet card. Okay, which means that it's costly lah to do this thing for certain component. Ethernet on the other side is cheap because every card costs about less than $35 each. This is EtherCAT easily more than $100 each per node. Okay, so there's the key differences. There is costing differences. It's possible to make EtherCAT as good as Ethernet as good as EtherCAT by putting a thing called master clock. Okay, don't know the actual price. It easily more than $10,000. Okay, it's easily more than $10,000. The latest one, I'm not sure the price. I've seen some of the thing. The costing is about 10K or so and above. But where am I? Okay, so easily more than 10K. More than 10K. 10K for master clock. Okay, for the Ethernet. So if you want to compare this thing with EtherCAT. Okay, so we are talking about real time lah. So what is this new thing? Is this is inside the Ethernet? This is known as a TSN network, time sensitive network. Okay, this is something new lah. Okay, it used to be this but why not go for this, and why people are building this? Because Ethernet itself, the end of the day, in IT, too many people are using this. Number one, just everybody using this. This thing, as I mentioned, the costing, it is $100 each, and as you add more and more, it get very, very expensive, right? And it is not a common protocol, and if you want to train people to do this is going to be hard. Internet on the other side, because of IT, a lot of people are using this. So people are trying to, from the IT angle, move in to do time-sensitive network and everything. Okay? I think eventually the master clock, the price will come down lah. Depends on how the thing is. Okay? Eventually we need the real-time communication to take place. So we're talking about local area network. The same thing applies for Wi-Fi. So we don't know when Wi-Fi will kick in for this. Wi-Fi, if you talk about, if you know that there's a Wi-Fi 1, Wi-Fi 2, Wi-Fi 3, Wi-Fi 4, basically this is 802.11b, this is 11a, this is 11g, the standard lah, this is 11n, this is 11 AC, AC actually have 2 band, and then number 6 is 11AX. Okay, this is the current one that most people are talking about, and then there's a 7 coming out soon by Nokia. All these are Intel. Okay, so the AX portion, the 7 part is also talking about TSN network, and somehow or other they want to put it into a thing called 6E enhancement of 6, because I think there's some problem with doing 7. Nokia is struggling with 7, so there's a 6E version. That's the way they want to do it. 7 I think is overly ambitious. Okay, 6 is already widely used, so they just do an enhancement with a different frequency at 6 gigahertz. Okay, so it's possible because you need to plan out as a whole so. But then this TSN, the time sensitive network, is moving towards 6E, so that industry can use it. So that's the Wi-Fi part of it. Okay, for the channel. Just now I mentioned Wi-Fi, but it's never there. So there are many ICS protocol out there, right? It has been around for a long time. There are a lot of proprietary protocol, right? Some are published, some are, a lot of them are in clear text. They are not encrypted, so they are very bad for all these things. The newer one, they are just wrapped around with TCP/IP, but then TCP/IP does not improve the security because TCP/IP is not a secure protocol by itself. It is possible to put in additional security for this. Okay, one of them is example Modbus. So it's possible to have put in TLS with Modbus. Okay. Okay. So that's the at this stage, this is the one that mainly people are working on at this point in time, because Modbus is the most used protocol of this ICS thing. Okay, so there are many vendors you can see over here, right? So if you want to go through most of them, there's a thing called man in the middle attack. Someone can go in, tap in, read the message, and then hack through the message. And this is what actually happens. So Modbus is one of the oldest, as I mentioned, most popular ICS protocol because it's free, open, okay, simple, okay. It is like an application level protocol, okay. And then it allows communication people to be able to design, and it has a lot of open source code out there for people to run off. Okay, so that's what the Modbus is. You have a master, and you can have many slaves, and then you can do a control. You just go through TCP/IP, and you can send it to. It was early days design. It can be okay. It is early days found in various industry building, commercial building, infrastructure, transportation, energy application. Remember, all these are local area network. Okay, local area network. Ethernet, not for long distance control. Okay, and then it's a master slave lah. If you talk about Ethernet, we are talking about things like 100 meters or so. Okay, you can see the request. And then the response come back, right? So that's the animation of this architecture. So I hope it helps. So they have different kind. They have the original one is to ASCII, right? They're still there. It's over RS-232 or RS-485, right? Then they have a plus version that is proprietary to Modicom. Okay. Then there is a real, the serial version, which is RS-232 or RS-485. Okay, 486 lah. So the most common one, this is the RTU, the most common one that people are using. But then in today's context, most people are shifting towards TCP IP version of them. Okay, and then they uses this particular port file too. Okay, and it is possible, as I mentioned early on, it is possible to put in TLS, basically the security for Modbus. Okay, because people have already done it, because it's open source, so it is highly possible to do it. The issue is not about whether it can be done or cannot be done. The issue is whether vendor want to do it or not. Okay, okay. The main part is whether all your end device vendor are willing to spend time and effort to do this. That's all. Okay, it is highly possible to do this. The code is available. Okay, just whether they want to do implementation on this or not. Okay. Internally, okay, there is a application header. Okay, just drop into the system. Okay, there's a header and then there's a payload. Okay, and because they look at TCP IP as an insecure protocol and insecure transfer mechanism, end of the day, that's what this thing is saying. Okay, it's possible to do authentication, step 1, and it's even possible to do encryption, just like I mentioned, right? So you can use a login form, you can have a certificate. The certificate is the one that provide the encryption. Okay, that's the key part. Okay, that is the key thing. First of all, it's gibberish. You will not be able to do, right? It's also possible to do some form of access control inside the Modbus itself. So it's whether people want to do it or not. Okay, the take-up rate is very slow. Okay, but let's hope, because there's a lot of incident happening. So I think more and more vendor, and especially for the past 5 years, as the chipset, the costing of chipset comes down, I think more and more vendor is willing to put in the additional effort to make a secured Modbus out there. Okay. Okay. Is there other issue beside that? It doesn't have any CRC hash for determining. Okay, and it doesn't protect mail-form packet. Okay, so it's possible to send a denial of services and session hijack. If you do an encryption, then this thing is gone lah. This thing is gone. This thing is gone lah, because you encrypt mah. Right. So if it's not an encrypted packet drop, so provided the how the way the thing is being programmed. So you need to figure out how to do the portion on at the software end, okay, to do this dropping of packet to prevent things like Modbus flooding end of the day. Okay, so it's possible to do. It's just a matter of how the software has been designed internally. It is a piece of software. Do remember, when you talk about protocol, it is always a piece of software, and how much things additional you can put it in to protect the network itself. Okay, next we're going to go into distributed network protocol. Okay, so DPN3 is a distributed network protocol. It's a version 3 of it, meant to use in SCADA. Okay, it is widely used. Again, it is an open protocol, right? It's designed to support over a huge geographical distance. This is no longer LAN, this is for WAN, but it's a high level protocol, right? So it can run over your standard TCP/IP network. Okay, let's take a look. So this is the Scala network, and through that. Okay, so it has provide some feature and function that's missing from Modbus. Okay, it runs on TCP. It also support UTP. This is the port that you use. If you run TCP and UTP, it is always possible to modify that whole entire portion to allow to have encryptions. Number one. Okay. Number two, when you're doing that, it is always possible to add in additional feature to provide authentication and authorization. Okay, so it's just a matter of whether people are willing to do that or not. That's all, right? It's three, right? This is three. It's the third version, right? Then you can just add in all these things just for security sake, right? End of the day. So this is just telling you what are the issue with them. It is sent in plain text. Okay, subjected for hijacking, denial of services, and all kinds of that. Of course, there's no security with it. They were subject to anything and everything end of the day. Okay. So if you look at it, this portion is the DMP portion only. Okay. So it's possible to add in all the necessary security, which is applied to normal any TCP/IP protocol end of the day. Okay, so that's the portion on this DMP portion. Okay. So there are, security specification. Okay, and then and there is some of the newer thing that is added to it. So some of the security extension is possible to do it, right? And this, the assignment of the protocol or the port, not necessarily is the protocol and not necessarily the packet. So the device can use some of the device that actually, such as torrent, are also using 20,000. So end of the day, the DMP standard is mapped to this particular port itself. Okay, so it may have a collision with some other protocol in terms of that, right? So when you use a sniffer, when you see 20,000, you will know that it thinks that it's a DMP. It may be just a mid-torrent machine that's running in the background. Okay, that's what it says here, But the key portion, the more important thing is it is already comply to the IEC 62351 standard, right? So if the software is done properly, it should give you certain protection end of the day. Next thing, ICCP. Okay, it is a vendor independent standard protocol. It is known as also known as a Tele Control Application Service Element Tool, TASI2, okay, or ICCP. Okay, it's designed for real-time traffic. Okay, can be used for LAN and WAN. Okay, for various stuff. Okay, so it is a client-server communication connections. Okay, it allows managing of data. Okay, and it provides data transfer, and depending on the request, for example, a client can make a one-time request. The key portion over here is real-time. Okay, it's how real-time is. When you go over the WAN, you're subjected to network time protocol. Your LAN, as I mentioned just now, if you manage to put your network as a TSN network, okay, time sensitive network, which is using IEEE 1588, then you are running on PTP, precision time protocol. Then because of the clock, it's a lot sharper, allows you to run a lot more real time. This is still in terms of millisecond. Okay, your at most is Oops. Just give me a minute. Okay, we are still talking in terms of milliseconds. Okay, over here, for PTP, we are talking about microseconds. Okay, so there's a world apart difference, right? Most of the network out there is still NTP, network time protocol. Good enough for a lot of things, but then is it really real time or not? That's the question that a lot of people need to ask. Okay, especially over wide area network. So how does this thing works, right? The client can request a periodic transfer of data. Okay, when it needs, they just establish the connection and get the data over. So this is the connectivity actually look like. So I will request and get a response and report. Okay, again, is it on top of TCP/IP? Okay, so it depends on how far it can be done. So if some of the thing is done up with necessary security, then if you can put in authentication, authorization, just like DMP, okay, then it's a lot more secure protocol. And most important thing, the encryption need to be inside. So especially the TLS portion need to be inside there. Okay. The biggest issue here is as time goes by, people need to think in terms of not using TCP anymore. Okay. The reason is TCP is slowly phasing out, even for your web application, your HTTP. Okay. The design is people are shifting from TCP to QUIC protocol. Okay, I shall not go further than that, but then QUIC is highly related to the security protocol TLS version 1.3. Traditionally, up to today, very much HTTP or HTTPS is tied to TLS 1.2. But 1.2 has a lot of problem, right? So it'll be good if people break off from 1.2, but then which means that you have to take out TCP and shift the whole thing to 1.3, means that you also have to take out this QUIC protocol, which means that there is a need to have a lot of changes in the transport layer for dealing with this. I don't think any of this current protocol, whether it's Modbus, DMP, and ICCP is ready for this. There are some tests on Modbus, okay, that I know of. For ICCP and DMP, I'm not too sure that whether they are ready for TLS 1.3. Okay. Next, there's a thing called field bus, right? So we have LAN, WAN, and then we'll talk about field bus. Field bus is not just one protocol, it's a group of communication protocol. Okay, so it basically it has a control, so it can be in ring feature, it can be in branch feature, it can be in star feature, it can be daisy chain. I'm not too sure about this particular word, branch. Okay, I suspect this is a original document from whatever. I suspect this is bus, not branch. Okay, this is likelihood to be bus architecture. Okay, so it depends on how the thing is going to be running, because there are a lot of systems that at the end of the day designed in such a way that for hybrid system, to the endpoint they normally run a ring. Okay, because you want the device to run a ring for, in case any connection drop. Let's say any connection. Let's change the color to blue, and then let's say this connection is dropped here. So it's still possible to communicate this way and communicate this way. Okay, so that's why the power of ring, the redundancy, the high redundancy of this stuff. and then somehow or other this part is a bus architecture up. Okay, so there's a ring, there's a bus portion of it for the design itself. So it's possible to buy equipment that's like that for higher reliability. And then all the way here, then they have a star, and you connect to another bus, and then at the bottom here is a ring. Okay, so this is a typical design of this. Daisy chain is a lot less unless you have let's say you have one that is like that, and then you probably have another one. This is called daisy chain, another bars here, and then so that you can create another ring here. Okay, so that's how the thing is been designed in that way. One very important thing is, number one, you want to support for higher redundancy. That's why people use few bus. Okay, and then the topology looks something like that and already. Okay, and some of the protocol support this. Ethercat support something like that. Okay, Ethernet will have some problem. Ethernet a lot of time basically it just all star. Okay, Ethernet basically is star, right? There's no point of running bus. Basically, internally is bus. Then the ring portion, the most problematic part is the ring portion, on how to go about it, right? So yeah, so that part, there are no it's a device connect to a device, end of the day. So it likelihood is going to be Ethercat again, internally, okay. But it doesn't cause any issues, big issues for having a ring internally there, okay, because of reliability and low latency design. Few characteristics of the old way of doing a few bus you mentioned. It can be bidirectional, right? It can be multi-drop. Basically, this is the 485, this is 232, right? Okay, all these are few bus. This is a lump of everything, right? And I mentioned multiple topology. The modern one is star, ring. They still put branch or tree. It's a branch lah. Basically, it's a bus lah. Topology lah. End of the day. Okay. There's no branch. There's just bus topology. Because in the end of the day, the key part is, if you think about branch, is bus. Right. This is a bus topology. This is actually bus. It's not branch. Okay. And then who are doing communication first? Okay, so it can be random. So you need to go to the logical level. It's not just purely the physical design and all that. So few bus has several levels. At the lowest level, they can have a sensor bus network. Okay, least complicated. Level 2, you can have a device bus. Okay, it's not just a sensor itself, but then you have a various speed drive and motor control. Okay, so some of these things, it has some controller inside there for connectivity. Okay, so the sensor is connected to all these various speed drive and motor control. Okay, next is control bus network, where all the higher level data comes in, such as your PLCs and HMI. Okay, and the highest level, of course, is information network, the IT portion that allows you to do data monitoring, file management, and so on and so forth. Okay, these are the 4 level of network running. A lot of few bus are at this lower level are non-TCP/IP, especially these two. Okay, they're just non-TCP/IP based. Okay, whatever over here, level 3 and above are all TCP/IP based. If you talk about modern one, because you want to all these are just a connection between is basically all the serial connection. Okay, it's either RS232 or RS485. Okay, single drop or multi drop. Level 2 mainly is 485, and then if you go to the lowest level is 232. Serial connection, UART, that's it. Okay, there's no point of having this design over TCP/IP because the protocol is not so complicated at the end of the day. Okay. So in terms of OSI and fieldbus, okay, it's either this or this, right? Communication protocol, right? So you have their message and sub layer and the user layer at the end of the day. Okay. One of the fieldbus is Profibus, right? It's a standard by the German, basically Siemens, mainly Siemens, for the having a fieldbus. Okay. Specific design for high-speed serial. See, you note that serial. It's not possible to have security for serial. It just introduce you there's such a thing. Okay, you just can't have encryption over serial because it's a piece of hardware. There is no software actually really involved inside here. All right. So if you want to put in the encryption and also not, the hardware need to know at the firmware level internally within the chip itself. They need to know how to decipher that. Most people don't bother because it's such a low level system. Okay, at that level. So the same thing, and so they have a logical. These are some of the early days systems. So OMI bus support a bus feature that is using a logical token ring. So it's a ring feature that goes around and send. And they have a PLC, right? So that's what it does for this entire thing. But then it's not possible to have security for this at all. Okay, it allows you to connect all the various things together using DR protocol. Okay, so few bus messages, Profibus and Profibus automation system allows to communicate and do all these things, put everything together. Okay, so few bus is around, the famous one is Profibus. Okay, that you may see over the network, but for security's sake, it is not highly possible to have any cybersecurity protection here. Next, we come into OPC. OPC is Open Platform Communication. Okay, formerly known as OLE for process control. OLE is a Microsoft API. Okay. Okay, it allows then a lot of the system is running on Microsoft operating system. Okay, we don't talk about very low-end embedded system. There are a lot of engineering workstation, especially engineering workstation, are running on Microsoft even today. Okay, so the way they program that on the HMI, some of the HMI are also Microsoft. Okay, well, it's a trimmed down version of that. So they're using this API for communication, OLE. Okay, object link system. This is what we call object linked, object oriented embedded process API. Okay, that's what this OLE is. Then as time goes by, they don't want it to be just Microsoft alone for the API, so they go for they make it into an open standard, such as Linux can run, Mac can run, some other operating system for compatibility's sake. So the new name is called Open Platform Communication. not really Mac lah. Basically, Java is a platform, okay, and so that you can have a Unix and Java whatever not to connect to this system, okay. So the whole point here is okay, at a point in time, OPC is a set of specifications shared by Microsoft technology. Then COM, DCOM, distributed common object model, distributed common object model, object link embedded, and remote procedure call. So all this has been replaced with .NET technology, okay, and then therefore OPC standard that's based on COM and DCOM, referred by OPC organization and known as OPC class specification. Okay, they have been replaced by .NET. Okay, so this is the library. All these are API. The red, all these things are APIs. Okay, for doing all the necessary programming. The object, how to do the actual programming model. Okay, that's the early stage of OPC. Then the .NET part is basically, if you today start looking into OPC documentation, internally they're using SOAP, simple object application protocol. And for communication sake, within here, the design are using XML as the communication protocol, communication frame internally, which is what .NET is. Okay, so .NET is basically using XML. So OPC is actually using XML for communication. When you're sending message, they need to have a common way of communicating. Early days, there are no standard. Well, you can have a standard. You can do your own design, which is using Cobra, if you know what's Cobra. Okay, for the very even earlier one. But then the system doesn't talk to one another, so eventually people give out and then they switch over to XML, and that's where .NET comes in. Okay, this thing early days look nice, but then there are no real standards out there. Okay, so eventually people were doing SOA, that's what it's called, SOA protocol, SOA, system architecture, object architecture, will actually move into XML, because that was a standard in early 2000. Okay, early 2000s, when people talk about XML. Okay, and it defines the exchange and data for, it's a very complicated system that include data, value, time, quantity, or whatsoever not. Okay, the early days DCOM portion. Okay, and it has some historical data access specification and all that for OPC. And then time shifted to OPC UA, which is web-based. Okay, as I mentioned, .NET system. This is really when you shift over to XML. That's when it moved into 2008. So it's 100% to XML. This is pre-2000. All these are telling you it's pre-2008 in actual fact 2008. So this COM and DCOM are using basically their own. There's some compatibility issue inside here. Okay, so that is what the thing is. So they have come out their own way of doing a design. Okay, for OPC. Then XML comes in as a standard language, so that it's easier to design all the various language, so that it can support a lot of non-Windows platform. Okay, such as a few controller, cell phone, Unix, Linux, and so on and so forth. Okay. So end of the day, that is the preferred system today that people are looking at it. Okay, the main feature is when you're using the old system, the security is not really there. Over here, OPC UA is because .NET and SOA and XML, basically, if you know what is Web 2.0, right, and SOAP lah. So with that, this gives you a web service security. Okay, so it's possible to have an XML with app service security involved for the cybersecurity portion and make sure that all the context is properly encrypted. Okay, so that's where the advancement of OPC part of it. Okay, these are the claim, early days claim lah, right? And then it can compatible for whatever Windows machine is. Yes, if you're using a Windows Microsoft systems, so Microsoft is a proprietary, but then Microsoft is the key part that actually links everything out in terms of the driver portion, because it's very difficult to write driver end of the day. So it makes life easier for people to write driver because you use a standardized driver. So-called lah, end of the day lah. But if you understand how Microsoft run it, then you will say that end of the day, forget it, it's still as bad as it is, because Olay at that point in time is meant for your this Olay thing is meant for your Windows 3.1, okay, which is Win16 library, or at the most move into your Windows 95, which is your Win32 library only. At most is supported to here. It comes to a point of difficulty of support when Microsoft decided to switch over to Windows XP. Okay, this become very, very painful. That is why there is a movement to move towards .NET and using XML. Okay, the driver, the way to write the device driver, everything are changed. And then the communication protocol need to support XML now. Okay, XP runs a different way of writing a protocol. So it's a WinWX driver. So it's a way of writing their device driver. It's very different from Windows 95, and Windows 95 and Windows 3.1 are very different in terms of writing a driver. So people need to be highly skilled in terms of trying to write from here to here to here, and not forgetting that is in between there's a window NT. So there are a lot of it makes OPC makes it slightly easier, but then it doesn't really solve all the issues eventually, end of the day. Okay, but then today we are very much into this .NET portion lah, right? Okay, because there are more programmers that know how to do .NET programming. Cool. Okay, so it's possible to have this OPC server that allows you to communicate to all kinds of OPC clients and devices end of the day. So, and then the rest of other protocol, so-called all these protocol can sit over this OPC and carry over it. Right? Just translate into OPC and then over it lah, basically lah, all the transmission data. So we have covered all the necessary stuff within this lecture itself, okay? And all these are the things that describe common component, type, data flow, communication, and some of the common protocol itself. Okay, thank you very much. I will see you next time. Bye bye.